Math 242, Quest to College. I'm Joe Vasta, and we are going to cover 9.2 series. So what is a series? A series is a sum of numbers. And so that's not really that bad. That's what we'll be doing in 9.2. We'll be adding up some numbers. It's the notation that might confuse people if you've never seen this notation. This is called sigma notation. Other books might call it summation notation. That one's funner to say because it rhymes. So sigma notation, summation notation, and it has this Greek letter, which is a sigma. And it has this letter here, this little variable, which is called the index of summation. 1 is called the lower limit of the summation, and 5 is called the upper limit. So what are you going to do? Well, this says you're going to add up some numbers. You're going to plug 1. This is your start point right here. So this, let's label this, is where you start. And the top number is where you stop. And so you start with I equals 1 and you put it into that formula. So I'll write it all out for this one. So this is really 3 times 1 plus 2. Okay, since we are adding things up, we're going to say plus, and then we're going to go ahead and go up to the next integer, which is I equals 2, and we're going to put 2 into this formula. So this is 3 times 2 plus 2. And then we're going to go ahead and do the next one. So I equals 3. So this is 3 times 3 plus 2. And then we go 4. So we're working our way up to 5. So this is 3 times 4 plus 2. Am I going to have room for this? I think I will. And then we put I equals 5. This is 3 times 5 plus 2. And that's what this notation, that's what the sigma notation is. It's telling you to add some things up. So let's go ahead and add them up here. We have 5 for that one, because 3 plus 2. And then this one is 6 plus 2, so that's 8. And then this one is 9 plus 2, which is 11. 12 plus 2, which is 14. And then we have 15 plus 2, which is 17. And you might recognize this right here when we're going from 5 to 8 to 11 to 14 to 17. This actually looks arithmetic, but it's not a sequence, it's a series. And later on we'll talk about arithmetic series. So we add these numbers up, and what do we end up getting? This is 31, 41, 42, 50, 50. This looks like it's going to be 55. So that's what they're going to have you do at the beginning of your homework. They're going to give you some sigma notation, and they're going to say, hey, find the sum. So let's go to this next problem. Now our starting point is at 2. So, and our index of summation is not I anymore, but it is k. So we put k equals 2 into this formula, and I get 2 plus 1 squared. And then I go up to the next integer, so that's k equals 3. So this is going to be 3 plus 1 squared. And then, look, I'm already at my stopping point when I get to k equals 4. So this is going to be 4 plus 1 squared. Now, the sigma notation says that when you plug these numbers into the formula, you're going to be adding all those. So what do I have here? I have 3 squared plus 4 squared plus 5 squared. So this gives me 9 plus 16 plus 25. And so what do we end up getting here? 41 plus 9. So this one's going to give me 50. Maybe you've seen this notation before. It's used in statistics. It's used in calculus. It's a notation that's used in lots of technical classes. Let's go ahead and do the next problem. Here. So problem number 3, the summation from 6 to 8 of this formula here. There's a light switch. We talked about that with sequences. And so now I'm going to let P start at 6. So P is the index of summation. And when I put 6 in there, I get -1 to the 6th power. And then I have 6 plus 4. Plus, okay, so my next integer is 7. -1 to the 7th power. And then we have 7 plus 4. And all I'm doing is putting that into this formula here. We have plus, and now we're at our stopping point, which is 8. So I have -1 to the 8, and then we have 8 plus 4. Okay, so we called this -1 to a P a light switch, and it acts as a light switch. It's turning on and off and on and off. So -1 to the 6th is actually a +1 here, and then we have a 10. We have -1 to the 7th is a -1, and then we have times 11. So this is going to be -11, and then -1 to the 8th. Okay, so now it's back to +12. So it looks like our final answer, when you go 12 minus 11 is 1 plus 10. So this is 11. So this is how you do the sigma notation. Okay, we're going to throw this last problem in here. I did say a series is a sum of numbers. That's how we start off, just so you're not scared. But this is a series, and it's not going to be a sum of numbers. It's actually going to be a sum of functions or algebraic expressions in this case. So our starting point is at 0. Our stopping point is at 3. And there's more than one letter in the formula. The letter that we're going to be assigning numbers to is the n, and then the x is going to stay the way it is. So we've seen this kind of deal with sequences. So what do we have? We have 0 plus 1, so that is 1 factorial x to the 0 over 3. So that's what happens when I put 0 in for n. Plus, okay, now I'm putting n equals 1 in. This is going to be 1 plus 1, 2 factorial, and this is x to the 1 over 3, plus, now I'm going to put n equals 2 in. When I put n equals 2 in, I get 2 plus 1, which is 3 factorial. We have x to the 2 all over 3. And now I'm going to go ahead and put 3 into the formula. And that's going to give me 4 factorial x to the 3rd all over 3. And so, like, if you got a little confused, what I did is I put n equals 0 there, n equals 1 there, n equals 2 there, and n equals 3 right there. And I'm going to add those all up. And we'll also reduce the factorials here. So look at this. We have 1 factorial is just 1, and then x to the 0 is 1, so the first term is 1/3. 2 factorial is 2 times 1, which is 2, so I have 2/3 x. We're not going to put to the 1 power. And then this one's going to be 3 factorial is 3 times 2 times 1, which is 6 over 3x squared. And then 4 factorial is 4. 3, 2, 1. Multiplying them all, you get 24 over 3 times x to the 3rd. So I'm not going to box this because I have some unreduced fractions. So let's go ahead and clean up our answer, and we'll be done with this problem. So 1/3 plus 2/3 x plus 2x squared plus 24 divided by 3 is 8, 8x cubed. And that's my answer. So my answer on this problem is not a number, it's actually a function. It's a polynomial. And so they study this kind of stuff in calculus, second semester calculus. And there are some really unfriendly functions that you cannot take the antiderivative of. You cannot use your antiderivative gun on, and right now you probably shouldn't understand what I mean by that. But one way you can find their antiderivative is to trick those unfriendly functions by writing them out as a series. And then you trick them, and then you can zap them with the antiderivative gun, and it's called infinite series. We will not be doing that in here. We're just learning sigma notation. Let's move on to the next kind of problem. So we've done 4 of these kinds of problems, and our next kind of problem is right here. So we're going to do it the other way around. They're going to give you something with numbers in it, and they want you to rewrite using the summation notation. Or they could have said rewrite using sigma notation. It's the same difference. So I'm going to go ahead and put the sigma notation up here. Okay, so we'll just put it right here. And I have to pick a letter. What were we calling them before? We were calling them the index of summation. So I'm going to make the letter be k. Okay, so here it is. K equals. Now, there's many ways I can present the solution here. I'm going to try to do it the way that most people would do it. In each of these terms here, I see something. What do I see? I see a square root. And so my formula is going to have a square root in it. Okay, now, when I do that, I'm going to have to put something under that square root, and it's probably going to be a letter, and probably the simplest thing that you can come up with is, hey, just put a k there. And so if you do put a k there, then our starting point has to be k equals 5. Where's our stopping point have to be? Well, we look all the way right there, and that's going to be k equals 40, so we put 40 up there. Now, if you're looking at this and saying, okay, well, we finished because we have root 5 plus root 6 plus root 7 plus root 8 all the way up to plus root 40, we can see that it's not exactly this. Right here, we have our signs alternating between plus, minus, plus, minus. So what we're going to have to throw into this formula, and I try to leave room for it, is a -1 to the k power. I always start off with that and see where that gets me. So if I put 5 in there, I end up getting square root of 5 times a -1 to the 5th, so I get negative root 5. And if I put, which is not what we have, and I put 6 in there, I get a positive root 6. So it seems like I've got my light switch on upside down. So how do I fix this? There's a few ways. The simplest way is to, in the exponent here, put a +1. And that should fix it, because when you put a 5 in there, you have -1 to the 5 plus 1, -1 to the 6th, which gives you positive root 5. And then you put a 6 in, and you end up getting -1 to the 7th, which is a negative root 6, etc. Another way of taking care of this is writing in the exponent k minus 1. So there's your answer. It's not unique. Now, when I say it's not unique, it means that maybe if you're working with a friend, they may have decided to start their k at 1 or even 0. Now, if you start your k at 1, you can't. So we're done with the problem, by the way. So some of you might want to fast forward to this problem. If you start your k at 1, you can't just put a k there, because then that's the square root of 1. You need the square root of 5. So I'm going to go k plus, what's going to take me up to 5? 4 more. Okay, and then you got to make sure you get your stopping point correct. Maybe I'll go up to 36. Let's see, 37, 38, 39, 40. Yep, and that gives me the square root of 40. And then my light switch, -1 to the k. Let's see, that's going to put a negative for the first term, so I'll go +1. Okay, so this, I mean, we could start our k wherever we want. Most people are going to do this. So the people who like to start their summation at 1 probably say, well, I like that better. But it doesn't matter. Both of these representations will give you that sum right there. Let's go ahead and do problem number 2. Maybe you want to pause the video and see if you can do problem 2 on your own. Okay, so here goes problem number 2. See, the difference between 1 and 2 is problem 2 has an x in it. Okay. Now, we kind of see the same form in all of these terms except the first one. See, all the other terms are fractions. When the first one really is a fraction, you can always go, this is over 1. Okay, so now I'm going to go ahead and write a summation. And we'll do k again. K equals something. Let's go ahead and take a look at the form of each of the terms. They look like a fraction. It looks like there's an x to some power on the top, and on the bottom it looks like 1, 2, 4, 8, 16, 32. Okay, well, on the top, what I have is a power, and it looks like I have a 10, and then the next one's a 13, and then the next one's a 16, and 19, and 22, and I'm writing it as a sequence here because I'm trying to get you to recognize this as arithmetic. This is an arithmetic sequence. And when you put pluses there instead of commas, it's an arithmetic series. Now, we had a formula in 9.1. You know, your A1 is 10 and your D is 3. And so you can use that formula. And I also showed you another way that I said, okay, well, I see the gaps are 3, so I'm going to go ahead and put a 3K there. And then I have to adjust. Let's see, if K starts at 1, then I'm at X to the 3rd. And I'm like 7 below where I need to be. And if K equals 2, I'm at X to the 6th, and I'm still 7 away. So how can I catch up there? I'm going to go plus 7. So I put 1 in there, I'm at x to the 10th. I put 2 in there, I'm at x to the 13th. I put 3 in there, yeah. So it matches up. My stopping point, let's see, I have 1, 2, 3, 4, 5, 6. My stopping point will be k equals 6, but you can double check it by putting 6 up there. I have 18 plus 7, which is 25. Now, if you were not satisfied with that, there was a formula that we did in the last section, which said a sub n equals, what was it? It was a1 plus n minus 1 d. So a1 is the first term. I'm just showing you another way to get the 3k plus 7. So this is 10 plus n minus 1 times d is 3. So this gives me 10 plus 3n minus 3. This gives me 3n plus 7. And of course, our n is not really n. I mean, we chose k, so that's what we have there. Now the bottom, 1, 2, 4, 8, 16, 32. That happens to be a geometric sequence when you write it with commas. So the way that I would do something like that is I could see that those are powers of 2. So I'm going to write 2 to the k. But then I realized when I put a 1 in there, I end up getting 2. I end up getting this one right here. And I put a 2 in there, I end up getting this one. So I'm kind of off by 1. So I'm going to subtract 1. And so when I put a 1 in there, I get 2 to the 0, which is that. I put a 2 in there, I get 2 to the 1, which is 2. And I put a 6 in there, I get 2 to the 5th, which is 32. And so, looks like I have my formulas. If you didn't like how I tweaked that to get the answer, you could look up the formula for the geometric series, which I believe is a1 r to the n minus 1. A1 is 1 in this example, and r is 2 because you're multiplying 2 to get each term to the n minus 1. And so this is really 2 to the n minus 1 or 2 to the k minus 1. So the stuff that we learned about in 9.1 is kind of used for here when you're trying to find patterns for the summation notation. There's our answer. You can double check it by plugging 1 in and 2 in and all the way up to 6, and you'll get that series. So that is kind of what you're doing in your homework. Let's go ahead and do something weird here. Okay, the next thing that we're going to do is we're going to talk about a little boy named Carl Gauss. Okay, this is a long time ago. And the legend goes that his class was noisy and the teacher, you know, what was he, like 8 or 9, and the teacher said, okay, you guys have to add up the first 100 numbers, and then that will keep you guys quiet. And that was the punishment for the class. And then I think the legend has it that Gauss came up and said, oh, look, I'm done within a few minutes. And the teacher was perplexed. How did you get that? They had to check it. And so this is what Gauss had to do. So this is what he did. Okay, this is not what I came up with. Gauss said that, and maybe he didn't do this, but he said, okay, this is what I'm looking for. It's a sum. Well, I could go ahead and sum up these numbers, the first 100 numbers, backwards. So I have 100 plus 99 plus 98 plus yada 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 plus 2 plus 1. And that's going to give me the same sum. Okay, so he just wrote them backwards right underneath the top one. And then he said, okay, so when I do that, okay, if I add both of those equations, I'm going to get 2s equals, well, the first one gives me 101. And then the second one, 2 plus 99, is 101. And the third one, 98 plus 3. You're going to find out that each of those things give you 101 when you add them. So the question then is, how many 101s are there? Well, let's see. There were like 100 things, 100 terms on the right-hand side, so there's 100 of those. So another way of saying that is you could say, well, there's 100 101s. And that gives me what 2s is. So I'm going to go ahead and take that answer, whatever it is, 100 times 101, which is 101 followed by 2 zeros, and divide by 2. And that's how little Carl Gauss got the answer as quick as he got it. So this is really 100 times 101 divided by 2. And so you can divide that out. You can figure this out on your own. You would end up getting... You would not end up getting 500. Good thing I have this white out right here. You'd end up getting 5,050. Okay, so that was a good little story, or was it? I mean, is it a story we would tell our friends? Probably not. What I'm trying to do on these next few pieces of paper is do a derivation of some formulas, and then we'll put the formulas up. So what am I going to do? Well, I've got an arithmetic, and we're going to call it a series now because we're going to add them up. So arithmetic series where A equals A1, and then we have our common difference D. Okay, so this is what I'm going to do. I'm going to add up 5 of them. We could make this proof look a lot worse than it has to look. And all we're trying to do is justify why this formula is true. You don't have to do any of these justifications in your homework. So let's go ahead and rewrite this. A1 is A, so I'm going to write A there. A2 is really going to be A1 plus D, because that's what makes it arithmetic. You're adding the same number D each time. D is the common difference. We used that word in the last section. So this is going to be like what? This is the next term. A2 is A plus D. Okay, so that's A1, A2 is A plus D. Okay, A3 is going to be this last one plus another D. So it's going to be A plus D, which is A plus 2D. And then A4 is going to be this last one, A plus 2D plus D, which is A plus 3D. And then A5 is going to be A plus 4D. So what I'm doing right now is very abstract. You might not like it. You might want to skip ahead until you see problem number 1. Okay, so what I'm going to do is I'm going to rewrite this sum backwards like little Carl Gauss did. So look at this. This is going to be A plus 4D plus A plus 3D plus A plus 2D plus A plus D plus A. I'm going to do the same thing Carl Gauss did. I'm going to add them together, so I'll get 2s, add both of the equations together, and then what do I have here? I have 2a plus 4d. And then look at this, 2a plus 4d, 2a plus 4d, 2a plus 4d, 2a plus 4d. So obviously I can write this down 5 times, or I can just go 5 times that. So what does S equal? S is going to equal 5, and then we have, I'm going to do something weird. Okay, so before I divide by 2, I'm going to write this as A plus 4D. Okay, and then I'll divide by 2. Now why did I do that? It's because, look what A5 is. A5 is A plus 4D. So I'm going to write this as 5. A is just A1. Remember we said that? So this is A1 plus A5. And this is all over 2. Okay, so now what we want to do is we want to figure out, hey, when we have 5 terms, we know what happens. There's a 5 here. You're adding the first one with the last one, multiplying that by 5, and then dividing it by 2. So, excuse me there. Suppose your arithmetic series went all the way to n. Suppose it had n terms in it. Well, instead of putting a 5 here, we would put an n here, and then we'd put the first term, which is A1, plus the last term, which is AN, and we would divide by 2. So this is the formula which gives you the sum of the first n terms of an arithmetic series. And so all I've done here is I've wasted some of your life proving this formula that we'll use in our homework. Okay, we're going to do the same thing with geometric series. I'm going to go ahead and do another proof. You know, once again, if you don't like these proofs, it's a free country. Turn it off or fast forward to the example that starts off with a 1. Let's do a geometric series. And I'm going to go ahead and do the same thing with the geometric series. So let's say my geometric series looks like A1 plus A2 plus A3 plus A4 plus A5. My geometric series, I have A equaling A1, just so I don't have to keep writing A1 a lot of times. And then I have R, which is the common difference. Okay, so what I'm going to do is I'm going to rewrite this. This is S equals. So A1 is just A. The next term, which is A2, is really A times R. That's what makes this geometric. And then A3 is going to be A times R, so AR squared. A4 is AR cubed. And A5 is AR to the 4th. You want the arrows like last time? There's the arrows. How do you like those arrows? Okay, so that's what we have so far. Okay, so now what I'm going to do is I'm going to go ahead and I'm going to say, well, what would happen if I multiplied both sides of this equation by R? Well, on the left-hand side, I'd have R times S. And on the right-hand side, I'd have AR plus AR squared plus AR cubed plus AR to the 4th plus AR to the 5th. I'm actually going to write them down, but I'm going to shift them over here. So watch this. I'm going to go, this is going to be plus AR. I mean, that's this one times R, and I put it over here instead of right below. And then I have AR squared plus AR to the 3rd plus AR to the 4th plus AR to the 5th. Okay, so now watch what I'm going to do. And this is a pretty clever thing here. And I didn't come up with it. I'm going to take the top equation here. I'm going to subtract the bottom equation. Okay. So what do I end up getting? I get S minus RS. So let's write that down. S minus RS equals. Okay, so A minus 0 is A. But what happens to all these guys right here? Well, I'm not adding them. Remember, I'm subtracting them. So they're going to go away. Those are just 0. And then I have a 0 up here minus. So let's put parentheses around this equation. Minus an AR to the 5th. So this is going to be minus AR to the 5th. Okay, I'm trying to find out what the sum is, so I'm going to factor the S out on the left-hand side. So I have 1 minus R. This gives me, let's go ahead and factor the A out just so it looks nice. A, and then we have 1 minus R to the 5th. I did not have to factor out that A, but I did for stylistic purposes. And now my S equals A times 1 minus R to the 5th. This is over 1 minus R. And remember, A is just A1, so I'll put an A1 there. Okay, so look what happens when we sum up 5 terms of a geometric series. You end up getting this, and you end up having a 5 here. So if I were going to sum up the first 11 terms, the only thing that would change here is I would have an 11 there. So with a geometric series, if I sum up the first n terms, I'm going to have this formula, and the only difference is there's going to be an n there where the 5 is. So I have A1, 1 minus R to the n. This is all over 1 minus R. And so we have just derived the sum of the first n terms of a geometric series. Okay, so we did all these derivations. Let's go ahead and apply them to problems. And we have like about 4 problems to apply them to. And so you'll see things like this in your homework. So look at this one here. Look what you've got. It says find the sum. And this is unreasonable to write all those out. K equals 1 to 200 of this formula. So what I'm going to do is I'm going to write out a few of them. K equals 1, I put in there, and I end up getting 4. And K equals 2, I put that in there, I end up getting 3 times 2. 6 plus 1 is 7. And I put K equals 3 in there, and I had 10. K equals 4 gives me a 13. And so you might notice right off the bat, you know, to get to this one, it seems like you're adding 3. This right here is an arithmetic series. This 3 right here kind of is an indication that, you know, there's your D value, but you can just look at it from here. And so this is going to go for, not forever, it's going to take a long time to write all out. If you were to write out the very last term, you'd put 200 in there, you'd get 3 times 200 is 600 plus 1, which is 601. Okay, so when we have our formula for this, okay, so we've derived a formula. This is an arithmetic series. And you know, when I derived the formula, I think I wrote it like this. I wrote it like that. I'm going to write the formula a little differently. Instead of writing that each time, I'm going to say the sum of the first n terms is n, and then we have a1 plus a sub n. This is all over 2. Now your book is going to give you another formula. They're going to go ahead and replace the an with an a1 plus n minus 1d and write this another way where you don't have to have the last term. But I don't want to complicate things that much. I'll just mention that in case you're looking at the book. And so on this formula, what we're looking at, so this was the formula. We're looking at is s, well, not n, but s. How many terms are there here that I'm adding up? 200. You'd have to be careful, like if you're doing a problem that started at k equals 3 to 200, because then you wouldn't have 200 terms because you're starting at 3. But a lot of them in your book, you know, you'll get things like this. And so n is 200. We have a1 plus a200. This is all over 2. Okay, well, we know that this guy right here is a1, and this guy right here is the last term, a200. So we're going to go ahead and put that into the formula. So this is 200. We have 4 plus 601. This is all divided by 2. You know, at any point now, I mean, I can cancel this 2 with this 200. I end up getting 100 times 605. I don't even need a calculator here. Look, this is 605 followed by 2 zeros. So this gives me 60,500. And that gives me this problem. And it was a lot easier than adding all those up on a calculator or adding them up by hand. And if you think, oh no, that would have been just the same amount of work, then try doing a problem where it goes from k equals 1 to 2,000. Let's go ahead and do another problem. So here's a problem right here where we have, make sure that I'm reading the right problem. Yeah, we have k equals 1 to 50 of 2 to the k. So I'm going to write out the first few terms. The first term is 2 plus, and then I put k equals 2 in there, 4. Put k equals 3 in there, that's 8. Put k equals 4 in there, that's 16. And so you can see that this is a geometric series because you're multiplying by 2 each time. And I'm not going to write out all the terms because there's 50 terms, but the last term is going to be, and you're like, well, what is it going to be? It's going to be 2 to the 50th. Okay, so I'll just write it like that. So the sum, let me go ahead, so let me first say that this is geometric. It's a geometric series. And that the sum of the first n terms is something that we derived. That's the one that looked a little messy. A1, and then we have 1 minus r to the n, all over 1 minus r. So that is the formula. And in this case, we are finding what? S sub. How many terms do we have up here? We have 1 to 50. We have 50 terms. And so this is going to be A1, we have 1 minus r to the 50th all over 1 minus r. Okay, so let's continue. We should find out what our r is in this example. And our r in this example happens to be 2. It happens to be r as well, so yeah, I'm on a roll here. Okay. R is 2, because you're multiplying by 2 each time. So this S50 equals A1. Oh, by the way, this guy right here is A1. We have 2, 1 minus 2 to the 50th. This is all going to be over 1 minus 2. On the bottom, 1 minus 2 is a negative 1, which could actually go up top. So you can write this as negative 2, 1 minus 2 to the 50th. You can even bring the negative inside the parentheses if you'd like. But the deal with this problem is you wouldn't want to do this by hand. So like if you didn't have a calculator, you would just say, oh, well, that's what the answer is. But if you had a calculator, you could easily plug this into the calculator, and you would end up getting a really big number here. So let me write it down. This is what I got when I plugged this into the calculator. So do we even know how to say this number? There's your hundreds right there, and thousands, and millions, and billions, and trillions, and quadrillions. This is 2 quadrillion, and we're not going to say the number, but there is the answer. Okay, so with these formulas that we've derived, the problems are a lot easier when you recognize either a geometric series or an arithmetic series. Let's go ahead and do a few more problems. We're almost done with this section here. And so we have this problem right here. Okay, so this problem we have 2 plus 7/3 plus 8/3. So some of these things seem like they don't belong. You could write the 2 as 6/3, and then we have plus 7/3. So I'm just rewriting it plus 8/3 plus 9/3 plus 10/3 plus yada 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 all the way up to 35. We're not going to write that as 35/3. We are going to multiply top and bottom of that fraction, 35 over 1 by 3. So we'll get 35 times 3 is 105 thirds. Okay, so the next thing we want to do is we want to say, what kind of series is this? Well, looks like I have the same amount of gap between each of the numbers. In fact, what am I adding to 6/3 to get to 7/3? I'm adding 1/3. So D is 1/3. This is not a geometric, this is an arithmetic series that I'm trying to add up to. And for the arithmetic series, I have this S sub n equals n a sub 1 plus a sub n all over 2. Now, we could pull out that other formula that the book has, but we'll just use this formula. So there's a few ways of doing this problem. I just felt like using the whiteout tape. Wow, this is messy. What is happening here? Okay, so what I'm going to do is I'm going to pull out that other formula that I had from the last section that tells me the nth term of an arithmetic sequence. And the deal is, I know that the nth term here, I don't know what n is. That's the whole problem with this formula. I know what the first term is and the last term is. So look, but I don't know what n is. So I'm going to say 35, I'm going to replace that with an, and a1 is 2, and I don't know what n is, but I do know what d is. D is 1/3. Okay, so I have, this is just one way of doing the problem, may not be the best way, but if you're in my class, then you can go look in the book and see other ways of doing this. And if you're not in my class and you're watching this on YouTube, you get what you pay for here. So this is 99 multiplying both sides by 3 equals n minus 1. So it looks like n equals 100. That's good to know, because now I know n is 100. Here's a1. This guy right here is a sub 100. We know that because now we figured that out by this. So I'm going to go ahead and sum up the first 100 terms of this series here. I have 100, a1, which is 2, plus an, which is 35. This is all over 2. So this is 100 times 37 all over 2, so this is 3700 over 2, and 3600 would be 1800, so this would be 1850. So hopefully I did that one correctly. And so we've just summed up the problems using the formula for the arithmetic series. Let's go ahead and do this last problem here. This last problem, which is problem number 4, we have 1 minus a third plus a ninth minus something plus something. And so you could actually, on this one, you might be able to count up and see how many 3's this is. Like, you could say this is 3 times 3, which is 9, times 3, because we're thinking this is a power of 3, which is 27, times 3, which is 81, times 3, which is 243, times 3, which is 729, times 3, which is 27, and we have 8 there. Okay, yeah, so wow, that was a lot. 1, 2, 3, 4, 5, 6, 7. So this number right here is 3 to the 7th. Okay, so I don't know why I did that. Oh well, just for fun. Why not? Okay, so this is a geometric series where a1 is the first term, and r happens to be what you're multiplying to get to the next term. And look at it, it's alternating. That means the signs alternate. So r is not going to be 1/3, it's going to be negative 1/3. And in our formula, I think the reason I went ahead and did this is I want to know how many terms there are. And it, you know, be careful with saying 7, because you actually have, this is a 3 to the 0 here. So when you count them all, you have 8 terms that you're trying to add up. So if we're going to use that formula that I had written out here, which says a1 minus r to the n, this is all over 1 minus r. Let's see what we have. a1 is 1, then we have 1 minus r, which is negative 1/3 to the 8th. And on the bottom we have 1 minus negative 1/3. Okay, so what do I have? I have, looks like 1 plus, no, sorry, it's going to be 1 minus 1 over 3 to the 8. At this time, maybe I should pull out a calculator, and on the bottom I have 1 plus 1/3, which is 4/3. And so this is really 3 to the 8th minus 1, getting the common denominator on the top. We have 3 to the 8th and a copy dot flip. And so when I do a copy dot flip, I have a 4 there And I have, I didn't copy dot flip correctly, did I? Okay. So I have a 3 here, and a 4 there. And so let me just see what 3 to the 8th minus 1 is. 3 to the 8th minus 1. This is 6560. And, oh wait, yeah. What am I doing here? 60, so let me just, I think at this point, we can cancel one of those, so this becomes a 7, and that becomes 4 times 3 to the 7th all over 3 to the 8th minus 1. And so, you could work this out a little more. Like what I said, 3 to the 8th minus 1 is 6560. And then we have a 12, 4 times 3 to the 7th. Okay, and I think we can divide that by 4. And so I end up getting, so I divide out by 4 here, and this becomes 1640 over 3 to the 7th. So 1640. And what is 3 to the 7th? 2187. And so you get something that looks like that right there. So 1640 over 21. And your calculator, if you are using a calculator, lots of times they have the fraction buttons, and I should have probably already used that. Oops. It's too much for this calculator to handle, which is like 0.75 rounded. So it's almost 3/4. Well, in any case, that's how you do these problems. The last thing that I want to show you is sort of a bonus. You could probably stop the video right now. That was probably pretty boring watching me do some arithmetic. But I want to say this, and this will come up in calculus. But if r is between -1 and 1, then, so think about this, like if r was 0.5, and then you went 0.5 to a really big number, you can do that on your calculator. That's going to go to 0 as n goes to infinity. So like you can go 0.5 to the 10,000th power, and you'll see that it's really close to 0. Well, knowing that r to the n goes to 0 as n goes to infinity means that as n goes to infinity, that thing right there is going to go to 0. So they have something called an infinite geometric series. And we study this in calculus, the second semester calculus, that if your series goes like A1 plus A2 plus A3 plus yada 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 and never stops, then this is actually going to equal to that r to the n is 0. It's going to equal A1 over 1 minus r. And this is provided that r is between -1 and 1. So if that's the case, then this is what you'll be doing in calculus. You'll be adding things that look like this: 1/2 plus 1/4 plus 1/8 plus 1/16. So this is infinite geometric series where r is 1/2, a is also 1/2, a1 is 1/2. And when you plug that into the formula, you end up getting 1/2 over 1 minus 1/2. You end up getting 1/2 over 1/2, which gives you 1. So in calculus, you're going to be adding up things that go where there's infinitely many terms, and that adds up perfectly to 1. So that's where this is going if you're going to be taking a whole year of calculus. This concludes 9.2. Do your homework and have a good day.